So hello everyone, my name is Radu. I'm a master student at the University of Bonn, and I'm going to be talking about my master thesis project on covers of reductive groups. So first of all, let's give a bit of motivation. So what are these things? First of all, these are central topological extensions of the F points of a reductive group G by the nth roots of unity mu and c. And we care about these things because like even if you just care about the classical local Langlands correspondence, you end up with these sort of extensions of the absolute Galois group by G, by the complex dual group of G, which do not come from L groups of any reductive group. But then this cover theory that was proposed by Adam Spogan and Kaletha sort of allows you to speak about these extensions as L groups of covers. So that's why we're interested here. It gives us a bit of more leeway when we talk about functionality questions in the classical Langlands, local Langlands correspondence. Right, so my thesis is, like the topic is comparing two ways of constructing these covers. So the first one is given by Kaletha in his paper, and the second one is given by Ife in his paper. But first of all, let's just say, let's denote Cov G for the groupoid of these covers with the natural notion of morphism. This is just a commutative diagram where you put GF and mu and C, and then you can easily check this is a groupoid. And then in this talk, I'm going to explain to you how I try to compare these two different constructions of covers in my thesis. We have some assumptions there. So F is a non-Archimedean local field. We usually take F to contain all the roots of unity. Maybe this is not needed, but I'm still working out the details. So let's just assume this as well. OK. So we're starting with the Kaletha paper first. How does he construct covers of reductive groups? So he does this using this sort of pseudo-fundamental group, which is defined to be the Pointryne dual of this cocycle group. So we have the adjoint dual torus and the torus. So we take the hypercocycles, the second hypercocycles of this complex of gamma modules, and then we take the Pointryne dual, and we end up with a compact topological group. And then Kaletha constructs this universal cover first, this GF infinity, and then to construct covers by mu and c, you sort of take a character of pi bar of G, and then you push out the whole diagram along this character. And then you can classify the isomorphism classes of these covers by this second hypercohomology group, which is basically just Pointryne duality and the fact that it interacts nicely with N torsion. OK. And now things get a bit more complicated here. So Tasha's paper is very concrete, but when we go into Ife's paper, you need to work with a bit more machinery. So I'm not sure exactly how to motivate this, but here everything is a sheaf of groupoids on the étale side of F, of spec F. And I mean, these sort of groupoids can have some kind of group-like structure or with some kind of commutativity. So for instance, G is also a sheaf by its functor of points, and it's a E1 group-like space. And then we also have this kind of coefficient sheaf, A, which is mu n of C, just a finite abelian group, which ends up being a sheaf of connective spectra by the recognition theorem because A is abelian. And then we also have this classifying stack that I think we've seen before at this conference as well. And yeah, that's also a sheaf. So everything here is a sheaf. And then we define this, this notion of étale metaplectic levels before they were called covers, even though that's kind of confusing because they're not really covers. But that's what you use to construct a cover. So what is this thing there? It's basically just a pointed map of étale stacks from the classifying stack, VG, to the fourth bar of A, twisted by some Tate sheaf there. So, and then these also organize themselves into a groupoid, but now this is an infinity groupoid, and it ends up being a two-truncated space. And then you can look at its homotopy groups and try to match them up with what we have on the side of Kaletha. OK. So now let me tell you exactly how you get a cover from this scary thing that we saw before. So this is the so-called local evaluation. This is not really a functor because the first guy is a two-truncated infinity groupoid, and the second guy is just a normal groupoid, but it's still a map. And how do you do this? So you start with mu, this point in morphism of étale stacks, and everything is canonically pointed, so you can loop it to go from G to B3 of A1. Then you take global sections over F, and you end up with a map from GF to the global sections of that guy. And then you basically want to end up with a monoidal map from GF to B, mu, and C, and then take the homotopy fiber, And it just so happens that since the cohomological dimension of F is less than or equal than 2, then when you truncate this gamma F B3 A1 to the first homotopy level, then you get exactly B and C, and then you take the homotopy fiber, and that gives you an abstract extension, and then you also need to topologize it, and this is a bit complicated, so I'm not going to give you any details, but there's no topology up to that point there. There's some checks you need to make, so this homology, these homotopy group computations are basically infinity étale theory, but they're very classical. Okay, so that's how you construct this kind of cover. But now the idea is that, in Yifei's paper, he constructs a lot more covers than we have on Tasha's side. So in my project, the thing you compare with Tasha's construction is this part on the left. So there is a co-fiber sequence of sheaves of connecting spectra on spec F et al. And maybe let's say a bit about the terms. So the first term is the internal home in the category of connective spectra between pi1 of G seen as a discrete sheaf and the second bar construction of A. And then this quad thing there is just a discrete sheaf of strictly Weyl invariant quadratic forms on gamma. This is like a combinatorial object, but our comparison is only touches the first guide there, so the fiber over Q equals 0. How am I doing on time? Okay. Okay, so now, those are sheaves, so you want to end up in spaces to compare to something on Kaletha's side, so you also take global sections. But now the problem is, so even in his paper, I think Tasha sort of organizes these cocycles that we saw before in some categories, but it's only a one category, whereas on Yifei's side, we have a two category. So how can we compare them? We need some kind, either to truncate Yifei's category or to promote Tasha's category to a two groupoid. I choose to do that other thing because it allows you to keep track of more information. So that's basically the motivation for this object I'm going to introduce now, which is this two groupoid K and G. So what is this? Basically, this is exactly what you get when you take this internal home of this maps fiber and you take global sections over spec F. You get space. And then it ends up being isomorphic to this, but you can also see it as so to make sure it's the same object and the right object we need for this comparison, we also need to show that this is the right object on Tasha's side. So there's an explicit cocycle definition there on the slide, but maybe let's not insist on why that's the right thing. You can see this is the right thing because it gives you exactly the global sections over spec F of this maps guy. And how do you do this? So basically, it's also quite natural on the side of hypercocycles as well because it's given by the Dold-Kahn correspondence. So you take this hypercohomology complex from the dual torus going to the adjoint dual torus and taking n torsion. And then by the Dold-Kahn correspondence, this corresponds to a strictly abelian two-groupoid. This just means that it's, so if you see it as a space, it's commutative on the nose with no, the operation is not, there's no, the space of compositions is actually just one point. It's not just constructible. Okay, so that's how you motivate it. And then you can also compute its homotopy groups here. So this is also an easy just Galois cohomology computation. And you get, first of all, for pi 0, you can see you get the right thing because you get H2. And we remember we have H2 here as well. So this is morally the right object. And it's the right object in a precise sense because now we can actually formulate a compatibility statement about how these covers are related. So let's move on to this bit. So this is this comparison square diagram where here, so in the top left corner, I have this object that I introduced, and then that is going to map to the characters out of which Tasha builds his covers just by point training duality. So that's basically just pi 0 of my two groupoid. Then I have this map that Tasha builds where he just constructs the cover that I talked about before. But it also is isomorphic to the F point, to the global sections of this maps guy. So then I can also run the evaluation, the local evaluation map and build the cover on Yifei's side. And the main theorem of my thesis says that this diagram here commutes. So not only I have the right object on both sides, but even when I build the actual cover, I get a canonical natural isomorphism between what I get by going like this and like this. And now there are further refinements you can make to this picture. So in both settings, I mean, I think Tasho is a bit more concerned with a splitting over GSC of F. But the point is you can extract a splitting for both, sort of, on both sides. So you can promote this to a map into Coven split or something that comes with so the same category, but also with a splitting. And then these two splittings also match up. And then both papers, they talk about L groups and LLC for tori, like we talked in the introduction. So these two parts of the, like these two Langlands relevant concepts can also be matched up for the two papers, but this is a bit more complicated. So I think I'm going to stop here to leave some time for the questions. So yeah, okay.
Okay, thanks for the opportunity to speak here, and welcome to KIAS. So I'd like to report on a joint work that started from last year's Arizona Winter School. So the subject of this talk is mod P representation theory of p-adic groups. So I'd like to bring some fresh air to this auditorium by introducing this L equal to P picture and show you how interesting / strange this subject is. So let me fix some notation. F will be a finite field over QP, a finite extension over QP. And I'll write G for the GLN F, and K for the maximal compact, G bar for the finite quotient, and Z will be the center. So mod P representation theory of p-adic groups, part of it is quite parallel to the complex theory, but also part of it is very different from the complex theory. And here is a mod P analog of the Bernstein-Zielinski classification, saying that every irreducible, admissible smooth representations are induced from supersingular representations. So you do have a notion of supercuspal representation here, which is equivalent to this notion called supersingular. So they play the same role, but the definition of supersingular is really what plays the important role. So, and this result holds for any connected reductive group, not just for GLN. So what are these supersingular representations? I need to discuss general theories a little bit. So given irreducible pi, we can find some irreducible representation of this finite group G bar such that we take compact induction of this sigma and it surjects onto pi. So this may remind you of this Bushin-Okuchiko type theory that Alexander talked about on Monday. But one difference is that in the complex case, you often need to consider some small open compact subgroup of G and then its finite quotient. And that's quite complicated. But here, we always just consider this G bar, the finite quotient of maximal compact. So in that aspect, mod P theory is much simpler than the complex theory. Okay, and once we have this quotient, we can consider Hecke algebra. Then the Hecke algebra, in this case, is also just simple polynomial ring with n-1 variable. And note that I'm fixing central character throughout the talk for simplicity. And this Hecke algebra acts on pi by a character. And we say that pi is supersingular if these Hecke eigenvalues are all 0. In the other extreme, if all these Hecke eigenvalues are non-zero, then pi is going to be principal series. So it makes sense. This is some notion related to supercuspal. Okay, so what do we know about these supersingular representations? First, let me define this universal supersingular representation as a quotient of compact induction modulo this maximal ideal in the Hecke algebra. So every irreducible supersingulars are quotient of these objects. And for GL2QP, this is already irreducible and admissible. And this gives a classification of irreducible supersingulars for GL2QP. So we are very happy. And then once we go beyond GL2QP, this is very far from true. And in fact, this universal supersingular is very big in the sense that it admits infinitely many irreducible quotients. So it's not that it's not irreducible, but it's infinite length. And it's also non-admissible. And it is known that irreducible supersingulars are not finitely presented Because of all these difficulties, there's no classification of irreducible supersingulars available at this moment beyond GL2QP. And our result proves generalize this to GLN under certain technical condition on the set rate sigma that I call special, and I'll comment more on this technical condition. Unfortunately, this condition is quite restrictive. For GL3, our result applies to roughly half of set rates, and for GLN, when n gets larger, this proportion becomes smaller and smaller. But there's obstruction for that. Okay, so I would like to, so this is like representation theory result, but the way how we approach it is using Galois representation, and I would like to explain the argument from a categorical perspective. So I need to talk about the analog of par G in the L equal to P setting called Emerton Gee stack. And I'll only consider what's called reduced substack. So this should be thought of as a moduli stack of mod P Galois representations. And we know that there's a bijection between these set rates and these irreducible component in the reduced Emerton Gee stack. Categorical conjecture would imply that under some condition on sigma, the compact induction of sigma should correspond to a line bundle on this irreducible component. And that also suggests that their endomorphism rings, namely this Hecke algebra and this ring of global functions, are isomorphic. And this was proven in my earlier work. And this result is what allows us to reinterpret Hecke operators in a Galois theoretic perspective. So we can define supersingular locus and ordinary locus in this C sigma as vanishing locus of these Hecke operator and also non-vanishing locus of these Hecke operators. Okay, so let me draw some picture and show you how this looks like. For GL2QP, this C sigma looks like P1. It's not P1, but it looks like P1. And the point at infinity corresponds to an irreducible Galois representation. And outside of that, all the Galois representations are reducible. So you have this one-dimensional family of reducible Galois representation that's specialized to irreducible Galois representation. And here, the ordinary locus is everything outside of this infinity, and the infinity is the supersingular locus. But what's more interesting is that there is another one-dimensional family of reducible Galois representation that's specialized to the same irreducible, and they form another irreducible component. So these two irreducible components intersect at this single irreducible Galois representation. So again, if you believe in categorical conjecture, on both components we have some line bundle, and then there's an intersection. So if I take a fiber at this point, you get something like a skyscraper shape at this point, and they're the same. So the representation theoretic incarnation of this is that universal supersingular for sigma and sigma prime, we know that these are irreducible because this is GL2QP, and they are isomorphic. And this is exactly the supersingular representation corresponding to rho bar under mod P local Langlands correspondence for GL2QP. Okay, so this is for GL2QP, and what happens if you go one step further for GL2QP square, then the irreducible component looks like product of P1. And so we have this square, and the edges should be thought of as P1. And the ordinary locus is A1 cross A1, again, given by this family of reducible extension, which is now two-dimensional. And then outside of that, we have another family of reducible representations. So on the diagonal, we have two families corresponding to 2P1, which are the same on the diagonal, but their extension are in the opposite direction. And the bottom and the top vertices are irreducible Galois representations. So here, again, supersingular locus is now this red part, ordinary locus is the rest. So again, this red family of ordinary representation, these are part of two-dimensional family coming from another irreducible component. So there's another irreducible component over there, and I'd like to choose rho bar in this intersection. And such rho bar is supersingular with respect to this weight sigma, but it is ordinary with respect to this another weight sigma prime. So one thing I should have mentioned is one difference, again, to the complex theory is that in complex theory, when you have different types, different types give you different irreducible representations. But here, different set weights can give you some same irreducible representations. So they have lots of interaction, and this interaction is reflected on this geometry because these different irreducible components have large intersection. So again, representation theoretically, it says that we have some candidate for mod P local Langlands in this case, again, denoted by pi rho bar. And we have a map from compact induction of sigma to it, which vectors through this universal supersingular, because our rho bar is supersingular with respect to sigma. And we also have a map from compact induction of sigma prime that maps into pi rho bar, but vectors through principal series. And the non-trivial part is this map. There's a map relating something about sigma prime and something about sigma. And this diagram, this commutativity of the diagram shows that this principal series realized as a subquotient of universal supersingular. But then I have infinitely many rho bar, so I get infinitely many principal series as subquotient here, and that's essentially what gives the non-admissibility and infinite length property of this universal supersingular. Okay, but then what is this non-trivial map? This is given by weight cycling. So this is proven by Emerton Gee and slightly reinterpreted by myself and Daniel Le. And it says that once we consider compact induction of sigma modulo some Hecke operator, it admits surjection from another compact induction where this Ci sigma is some explicit finite length representation of finite group. This is essentially given by parabolic induction in finite group, but and then we can ask whether it's irreducible subquotients, and this is well understood for GL2 or GL3, but beyond that, it's not so well understood. But a consequence of this is that we can also have a map from this compact induction of Ci onto universal supersingular, and so this is what we want to study, and this is something more concrete, and that's how we would like to approach to this universal supersingular, where the difficulty is that we do not know very much about this Ci sigma, and also this cycling map is quite hard to understand. And what I'm trying to do is, again, I bring Galois representations so that I kind of cut out these big objects. It's like, again, something like you have these sheaves on Emerton Gee stack, and I take fiber as some single Galois representation so that it becomes smaller and easier to analyze. Okay, so here's a proof strategy. So for GLN now, we would like to find some auxiliary setaway sigma prime and a Galois representation such that my Galois representation is supersingular with respect to sigma, but ordinary with respect to sigma prime. And that's, but we need something more. We need to exclude some other set weights that possibly appear in this Ci sigma. And once I have Galois representation with this property, I can run sort of the same argument. But the technical part is basically these conditions will define some locus inside of this Emerton Gee stack. And I need to show that such a locus is not empty. And that's non-trivial, and that's not always true if I do not put assumption like this special sigma being special. And also this sigma being special, this sigma prime is essentially given in the definition of sigma being special. Okay. But yeah, once I have a Galois representation like this, I can run a similar argument. I cannot understand this cycling map directly, but I can find some subquotient of it, subquotient of this Ci sigma with some map induced to pi rho bar, and that again vectors through this principal series. And I have infinitely many such rho bar, so this would realize this principal series as subquotient of universal supersingular. Okay, so again, existence of such a row bar is the most non-trivial part, and this is proven by using explicit local chart of the Emerton Gee stack studied by Le Hong, Mora, Park, Chen. And let me finish with the last remark that we expect, in fact, this whole compact induction of sigma prime lives inside of universal supersingular. And this is very bizarre. I mean, it's very counterintuitive because this universal supersingular is quotient of compact induction of sigma. So we cut out a lot to get this universal supersingular, and yet it contains another compact induction as a sub-representation. So this compact induction has some kind of fractal-like structures. And this was verified for GL2 by Stefano Mora when f is not equal to 2, not equal to QP. Okay, I think I'll stop here. Thanks for listening.
Okay, thank you very much for the introduction. It's my pleasure to be here to introduce my recent work with Heejong. So the topic is about extensions of p-adic stochastic. So we study the geometry of Schumann varieties. So in this paper, we, rather than solving a specific problems, we try to introduce some new notions and show that it's a useful notion. So let's fix some setup. We consider Schumann data, and we fix a prime P. We take the local field E above the fixed place. And we take a smooth model of G, which is a smooth affine group scheme. And we fix the level at P, and we let away from P level to be sufficiently small. Now we can consider the tower of Schumann varieties. We want to study certain integral models over OE. So there are many meanings of integral models, and we. Sorry. Okay, so we need to know what is a good integral model. So we will follow the Papas-Rappaport's notion. So following Deling's philosophy, we expect the Schumann varieties to be moduli spaces of motifs modulo some assumptions. Schulze suggests that it might be useful to instead view Schumann variety as moduli space of certain Stuka over Z. But now we can only define Stuka over ZP, and we will study in this way. Papas-Rappaport, they post a contractual framework for integral models, which says, given the paraholic level structure, then there should be a system of normal flat integral models such that it satisfied an extension property, and the G-Stuka on the geometric fiber will extend to the integral model. Here, the PKE comes from the Durand pro-étale torsa, where you pull back the level at P. And it should locally be isomorphic to integral local Schumann varieties, which is Rapporting space. And in the same paper, they show that if such a model exists, then it's unique up to a unique isomorphism and enjoys good functionality. This justifies the name canonical integral models. In the same paper, and also by Daniel Houghton, Kim Zhang, and Daniel Siukas, given the host type Schumann data, or more generally, given an abelian type Schumann data, but we need P bigger than 2 and G is paraholic, such a family of canonical models exists. In Danielson and Yuka's work, when they consider abelian type Schumann data, they use the Kisin-Papa-Zhou's construction where the condition P is bigger than 2 and G is paraholic is included. So they need to post this condition. Now let's briefly recall the commodification theory. On geometric fiber, this was studied by Bailey, Brown, Ash, Manfred, Rapporta, and Pink. On the integral basis, it was also studied by many people, by Deling, Rapport, and Faltings, Langkai, Manapusi, and Heejong, the second author, and also others. So to summarize some of the important properties, given the Gx to be an abelian type Schumann data, we take P level to be arbitrary level, and we do have normal proper flat integral models for toroidal commodification and a minimal commodification over OE. They contain the SK, the interior Schumann variety, as an open dense subscheme, and you can describe the boundary in a very satisfied manner. So it has the axiomatic description summarizing Lang and Shaw's work. Now the very natural question is to ask, how do we understand the commodifications in the Papas-Rappaport setting? For example, how do we study their canonicity and functionality? So our observation is that the boundary strata of the toroidal commutative, they carry more structure than merely being normal crossing devices. So to be more precise, étale locally, you can view the toroidal commutative as the commutative of some mixed Schumann variety. In the zero case and more general PO type case, this mixed Schumann variety, there are moduli spaces of some degeneration data. So this boundary mixed Schumann variety, they have integral model that should also be characterized by partial pole excellence. So in our paper, we first defined the notion for canonical integral model for mixed Schumann variety. And then we define the integral model for canonical integral model for toroidal communication to let it first has a good qualitative description as the one summarized by Lang and Zhao. And then we require for each cusp label, the mixed Schumann variety at boundary, they should satisfy Papas and Ropo's axioms in a certain sense. And we also define the minimal quantification in the same spirit. So first we have to justify the name. Why do we call it canonical integral model? So we prove that such model for mixed Schumann variety, for toroidal communication, for minimal communication, if they exist, they're unique up to unique isomorphism, and they have good functionality. So we call this canonical integral model. Second is the existence. So we show that in a very vast generality, we prove that for any abelian type Schumann data, for any prime P, for any quasi-paradox level, this canonical integral model, they all exist. So as a remark, if you take the cusp label to be Gx, this gives you the interior Schumann variety. This already extends the known result I just recalled. So we can deal with the P is 2, and we can deal with arbitrary quasi-paradox level. I think this is very useful for reference. So given the existence of canonical integral model, Papas said there is a Stuka map. This is included in the axiom. Now, given canonical integral model of toroidal communication, we also aim to obtain a log map, a log Stuka map. So we construct that as a consequence of the canonical integral model instead of an axiom. I will now introduce the definition of log diamond and log Stuka. Rather, I will show you some favorite theorems about that. So let's recall in Papas paper, given a scheme over ZP. So first we can construct a V-shift, a diamond associated with X, which is a V-shift. Given a G Stuka bounded by mu on the generic fiber, the show is equivalent to give a pro-étale torsor together with a host taper map. On the special fiber, it's a crystalline object. And moreover, it has the rigidity for extension. So this means if you have a morphism between Stukas over X, then the morphism, the restriction to the generic fiber is full faithful. This is very convenient when you want to construct the tensors from the generic fiber to integral model. We do something parallel. So now the object will be a log skin, a FS log skin. This is a very typical assumption in log geometry. You can think about normal crossing devices. We can also consider a log diamond. We learned this notion from Koshikawa-Yao's paper, but our treatment is slightly different because we define that as a V pre-stack, and it's a very difficult theorem to show we actually have a V stack. Given a log G Stuka bounded by mu over this V stack, so over the generic fiber is equivalent to give. Now, because we have log structure, we cannot just consider the pro-étale thing. We have to consider the pro-Kummer-étale with some actual conditions. Pro-P-Kummer-étale torsor together with a host taper map. On the special fiber, we show that the log Stuka will eliminate all the monodromy. So it will become an actual Stuka on the special fiber. So in particular, you will have a crystalline object. And it also has a rigidity extension. So assume the existence of the canonical integral model for toroidal communication for arbitrary quasi-paradox level, then we construct a unique log G Stuka bounded by mu on the log diamond, which extending the one on the generic fiber. So on generic fiber, you can pull back the level at Kp. Then you have, by Diao and Liu Zhu's work, you have a pro-Kummer-étale torsor with good monodromy, and you do have a log G Stuka on the general fiber, and we show you can extend to the integral base. The construction here does not rely on the abelian skins or p-divisible groups, because we only assume the canonicalness of the integral model. Yeah, but abelian schemes and p-divisible groups are needed when you verify the contractual framework. There are, we will mention two important corollaries, which are new result, I think, even in the modular curve case. So first, as we said, if you take the special fiber, the monodromy will be eliminated. So you do have a globally defined Stuka on the special fiber. Second, you can restrict your log diamond to the big diamond of your integral model. This will extend the one on the diamond slash constructed by Papa-Jean-Robert. Another very important aspect is about degenerations. So we can describe the degeneration of Stukas along the boundary. This is actually our starting point. To be more precise, as we said, the formal behavior along the boundary can be characterized by mixed Schumann varieties. So if you take an affine open formal scheme, then you take spec R, which has morphisms to both base scheme. Then here is our degeneration diagram. This tells you how the log Stuka on the Schumann variety degenerate into the boundary. How does it relate with the weight filtration and blah, blah, blah. In China Faultings and Langlands' work, they describe the formal completion along the boundary. Using the Mumford's construction, they use the degeneration data. You can think this theorem in that spirit. So a theorem following this is we can show all the strata, various strata on the special fiber, like the Newton strata, central leaves. They're well positioned, which means they behave very well along the boundary. And their toroidal commutative are actually the fibers of this Stuka map on the special fiber. So they have very good commutations along the boundaries. This is very useful when you consider the non-proper Schumann varieties and study the geometry of the special fiber. So this notion, this language has many useful results. I will only, because of the time limit, I will only introduce two, which might be more relevant to here. So first is a very natural question here. So in my Kato-Yuka's paper, they construct the systomic realization, which follow with a Stuka realization. So a very natural question is to ask if this is compatible with known cases for log prismatic thing on smooth model on hyperspecial level. So whether this theory is compatible with Kochikawa-Yau's theory, and the answer is yes. Given the log analytic prismatic F crystal, you can attach a log Stuka on that, and is compatible with the étale realization. So Kantaro showed that given a smooth model of host type, so so we do have a log abelian scheme by the theory of Kajiwara, Kato, and Nakayama. So you can attach a universal log p-divisible group. Then you can associate a log prismatic realization and then a log Stuka realization. So this is one picture, and now it's not complete because in Kantaro's work, the boundedness condition by mu is not checked. So we will, together with Kantaro, we will study in this direction and to fulfill this picture on the log p-adic Hodge theory side. Another question might be more relevant to this conference is that why do we define log diamond as stacks in this way? So let me introduce my motivation. So first, given the Schumann data, for level KP, for simplicity, we assume G is GC. We expect that if you fix away from P level, there should be a collection of cone decompositions such that we do have functorial defined compactified Ibusa stack, as V stack satisfy the following two Cartesian diagram. So in this diagram, the left upper corner is the log diamond we defined here, which is defined as a V stack. So we do not increase the site, but we enlarge the sheaf to the V stack. So this should be the correct one to fit in the diagram. And this restriction of this compactified Ibusa diagram to the good locus or beyond good locus should be compactified with all the known results by Karani, Schultz, Sandos, Zhang, King, and Chanel, Daniels, Houghton, King, Zhang, and Karani, Hammond, Zhang. For example, if you take the generic fiber, you pull back the level at P, then this will tell you the fibers of whole state pure map is exactly the perfectoid Ibusa stack, the perfectoid toroidal Ibusa variety. And moreover, for this diagram, because it's defined over ZP, so you can take the reduction over FP. As we said, the log Stuka will degenerate into a Stuka. So you really have a schematic thing on the top row. So this will recover the classically defined toroidal Igusa varieties over central leaves. Okay. Yeah. So for PO type with hyperspectral level, we think we know how to work it out, and we are working on the host type the host type case. We think this might be a good formalism to think about if you want to work with the compatified Igusa varieties. Okay, and then is the summary. It's all of my talk. Thanks.
I apologize for the delay. Yeah, thanks for the opportunity to speak here. And today I'm going to talk about the spectral action in very metaplectic Langlands. The guiding principle throughout this talk is that if you have a vector space or a category which has an action by something commutative, then we can spread it over a space. And from our experience, we know that this is an extremely powerful method of studying the vector space or a category. If you have I suppose in this conference, we are spreading the category of smooth representations over the Bernstein Center. And yeah, if you have a commutative algebra R and its module, then you can understand the module as a quasi-coherent sheaf over the spec, and you can go one level higher. So if you have a stack, say X, and a category M with the action of QC X on M, then this module category M gives rise to a sheaf of categories over X. So this is what I mean by spreading an object over a space. In Langlands' program, we apply this guiding principle to the space of automorphic forms using Hecke symmetries. And in geometry Langlands, we study the category of automorphic sheaves, namely sheaves of Emerton Gee, using this Hecke symmetry. So the natural question here is, on which space does this category of automorphic sheaves spread over? Yeah, let me set some notations. X is a smooth projective curve over C, and sometimes we will conflate it with the underlying topological space of it. Let E be an algebraically closed field of characteristic 0, and G is a complex reductive group. And given a topological space, say K, we let sheaf K be the category of sheaves of E vector spaces. By considering the underlying topological space of the stack Emerton Gee, we get the category of sheaves on it, which we call AG. And we also have G check, which is the Langlands dual of G defined over the field E. Yeah, so it turns out that the category AG has a huge amount of symmetry. From geometrics attack, we have the Hecke action, which tells us that at each point of the curve, there is a canonical action of rep G check on the category AG. So in particular, this tells us that we can spread the category AG over the stack BG check. But this category has I want to explain this picture. This is the visualization of the action of the object V in rep G check at the point X. But in fact, this category has a much bigger symmetry because we can consider Hecke actions at different points and they canonically commute. So for example, if you chose two different points, then those Hecke actions combine into the action of rep G check tensor 2 on AG. And you can do it for more points. So knowing that AG has a huge amount of symmetry, we can ask what's the biggest symmetry acting on this category? The answer is provided by the following result. There's a canonical action of QC over log G check on AG which assembles all the Hecke actions. This canonical action is something we call the spectral action. And in particular, this tells us that the category AG spreads over the stack log-sys G check. Yeah, I'm just suppressing, yeah. Let me elaborate on this. Log-sys G check is the moduli stack of G check local systems on the underlying topological space of X. So this has a topological nature. And what do we mean by assembling the Hecke action? At each point of the curve, there is a canonical symmetric monoidal functor from rep G check to QC over log-sys G check, coming from the pullback of quasi-coherent sheaves. And the content here is that the pullback of the spectral action along this symmetric monoidal functor is canonically identified with the Hecke action at the point. The main goal of this talk is to discuss the metaplectic version of this result. What do I mean by metaplectic? This is in the context of metaplectic geometry Langlands, where we study the category of twisted sheaves of Bonn G. And these are organized into the category which I call AQG. Q here is a metaplectic parameter. I'm intentionally using somewhat vague name, but the correct definition is the metaplectic level introduced before. And yeah, this enables us to talk about twisted sheaves on Bonn G. So we can ask the same question: on which space does this category spread over? Why are we interested in this question? One of the motivations come from metaplectic Langlands program, which is the Langlands program for covering groups. In that area, we study the vector space of genuine automorphic forms. And the point is that sheaves on Bonn G are geometric analog of genuine automorphic forms. Yeah, to convince this slogan, let me make a quick digression to twisting constructions. So say that you are given an abelian group A, and if you're given a vector space with an asymmetry, you can twist the vector space given an A torsor. You can go one level higher. So if you have a category with an asymmetry, then you can twist the category given an A gerb. So if you're unfamiliar with the notion of gerb, this is just the one categorical higher analog of torsor. The formation of sheaf category is of a local nature, and it has a natural E-cross symmetry. So E-cross is a group of units. Just because our definition of sheaves are sheaves of E vector spaces. So doing the sheafy version of the twisting construction, what we get is that given an E-cross gerb over some space, you get the category of twisted sheaves on that space. So a metaplectic parameter can be defined in several different contexts. And in geometric context, it gives you an E-cross gerb on Bonn G. So you can talk about twisted sheaves on Bonn G. And in the arithmetic context, it gives rise to a topological covering group of the groups like GF or GA, where F is the local field and A is a ring of adels. So you can talk about like the concepts like genuine automorphic forms or genuine representations. For example, there's a particular metaplectic parameter which recovers the usual metaplectic covering group of the spin group. Yeah. So yeah, you can see the general parent here. So given a metaplectic parameter gives rise to a data of twisting over a certain space, and you're going to study the twisted objects. Yeah, one quick comment is that you can also formulate a metaplectic version of Farc-Joseph program using this parameter. Yeah, so we had the following question, on which space does the category spread over? And the result I want to introduce today is that there is a canonical action of quasi-coherent sheaves over a certain stack on this category AQG. What is this stack? From the data of the group G and the parameter Q, you extract two data. The first one is the metaplectic dual group, which is a reductive group over E. And the second one is a metaplectic dual gerbe, which is a certain gerbe over the curve X. And the stack of local system, this stack is the moduli of twisted H local systems on the curve, where the data of twisting is given by this dual gerbe. Yeah, so from now on, I'm going to explain some ideas behind this theorem. And to do so, it is helpful to look back to the untwisted case. In the untwisted case, remember we had this following spectral action. And it turns out that this spectral action follows from the general framework of categorical framework of factorization homology. Suppose we have a symmetric monoidal category A and a category M and a topological space, say Y. And suppose that for each finite tuple of points in Y, we have an action of the tensor product of A on this category M. The example we want to keep in mind is the Hecke action, where the symmetric monoidal category is rep G check, and this module category is AG. Yeah, for example, if we chose the tuple x comma y in the curve, then this is a visualization of the action of V box tensor product W in the category A tensor 2. We say that this collection factorizes if it has the following two structures. The first thing is that the action act Y depends locally constantly on the choice of the tuple. And the second one is a certain compatibility between the multiplicity of the tuple and the symmetric monoidal structure of A. What do I mean by this? So we had the following visualization of the action. And you can move around the point X and Y, and the resulting action would depend locally constantly. So we can move around points like this. Yeah, and it can happen that those 2 points collide. And the second structure tells us that the effect is the same as taking the tensor product of those two objects. So those 2 points collide, and then this becomes this diagram. In this situation, the categorical result is that there is a symmetric monoidal category called the factorization homology, which acts canonically on M. Furthermore, it assembles every actwise. What do I mean by assembling? It's very similar to what I meant by assembling in the spectral action. So at each tuple of points, there's a canonical symmetric monoidal functor from the tensor product of A to the factorization homology. And this functor is called the insertion functor. And the content is that at each tuple, the act Y is canonically identified with the pullback of the factorization homology action along this insertion functor. There's a multiple point version of this Hecke action, and you can prove that the multiple point Hecke action defines you a factorizable action of rep G check on AG over the topological space of X. So from the general categorical framework, we know that the factorization homology of rep-G check should canonically act on AG. And now we conclude from the following identification of the factorization homology. Yeah, so let's focus on the twisted case. So what gets different from the untwisted case? We still have an analog of the Hecke action, namely the metaplectic Hecke action. However, there's a crucial difference. So there's not a single category that acts on every point. So what do I mean by this? In the untwisted case, there was a single category rep-G check, which was acting on every point. But this is not the case anymore in the twisted case. So in the untwisted case, you have a constant family of algebras over the curve, rep-G check, so valued in rep-G check. However, in the twisted case, you have a non-trivial local system of algebras in rep-H acting on this AQG. And the twist is, and the non-triviality of the local system is encoded by the metaplectic closure. However, this is the only difference because you can show that the metaplectic Hecke action factorizes in a suitable sense. So you can imagine developing a twisted analog of the factorization homology formalism before to attack this problem. We proceed in 4 steps. The first step, The first step is to define a twisted variant of factorization homology, where the input is an abelian group, a space, and an A-gerb over the space. And you start with a symmetric monoidal category equipped with an A symmetry. Second, we identify QC over the stack of twisted local systems with a certain twisted factorization homology. And we develop a categorical framework studying the action of twisted factorization homology parallel to what we did for the untwisted case. Finally, we proved that the metaplectic Hecke action actually fits into our categorical framework, and this requires some input from factorizable Satake, metaplectic version of factorizable Satake. So yeah, combining all this, we can spread AQG over the stack of twisted local systems. And one way to understand the metaplectic geometry Langlands is to, how can we describe the sheaf of categories? Okay, thank you.